Good morning to everyone. Hope you had great vacation with the New Year time, and wishing you Happy New Year for everybody celebrated there. Can somebody confirm whether I'm audible or not?
Yes, audible. Good morning and Subalu Tadaka.
SMU, Hamoto. Uh, let's start with the recap on the last few sessions, because we are starting a few weeks back, and let me recap on what we have learned so far. Today we'll be starting from 8:30 to 10:30 for the session 5, and then we'll be having 15 minutes break. Thereafter, we can have session 6, which is for the second session on today. And we started with the introduction on the course and the coverage as well. And I wanted to explain you that we will be covering not only the network equipment, but host level of networking as well, which is the coverage marked by blue color here. So we discussed some of the aspects in terms of latency, end-to-end latency on the last session. And that's quite covered in the host level networking, and as well as the network equipment and cabling levels, cabling as well. And then again, we'll be covering most of the enterprise networks as well as the data center networking in the first 6 sessions. Mostly overall coverage for the course module will be based on enterprise networking as well as the data center networking, where the ISP internet or service provider network will not be covered in detail, but there are certain areas which we will be covering in terms of ISP redundancy, and all those things will be discussed today. A bit of on the BGP as well, which is the border gateway protocol. And then we defined what's enterprise campus, and I set your goal on after this particular course, you should be having the understanding of troubleshooting a kind of a network built on enterprise campus, where why and getting the understanding of different components of here, and why we have been using duplicate devices or redundant devices, and fundamentals on the failure points. Those will be covered. And we discussed briefly on the network lifecycle. I haven't gone through the details because this has covered on your network design course on the first semester. But I wanted to give you an impression on the troubleshooting aspect based on the network lifecycle. And I have given a few different aspects by taking an example and life cycle as a continuation of network building and maintaining and fine tuning. And again, we discuss on the feedback loops. If there are issues on the one of the phases, you can always go back and rectify that. And we started with some reference books as well for those the separate modules. And I highly recommended on this computer networking top-down approach, and as well as the latest edition is 9th edition. I'm not sure whether it's available on your libraries, but the 7th edition is fine for this particular course. And then on the last week, which is on the 28th March, we have been covering the network troubleshooting approaches. Then we started on the troubleshooting fundamentals and fundamentals of network risk management on the second session. Then on we discussed on different network troubleshooting approaches. Started from top down, bottom up, and divide and conquer. And we discussed on the follow the path troubleshooting approach, which is based on the trace route application, and then compare the configurations. All those 6 troubleshooting approaches are quite important. Maybe this will be tested on assignments or in your final exams as well. So then we started on the network troubleshooting fundamentals. We'll be proceeding the subtopics of network troubleshooting fundamentals today as well. We started with the risk management, network risk management, then we discussed on this particular 3 types of exposures, fragileness, robustness, and anti-fragility discussed. Then the risk assessment by a quadrant and a rare event we have been discussing as black zone events. And then there are several reference books if you require to further reading and understanding in the details. Then we went on the session 3 as well on the last week, the week we had on the last lectures. Then we moved on to network complexity, network failures, control plane, data plane, and management plane, the 3 planes of network devices, and then separated the hardware and software failures and discussed the details. The complexity network defined as a complex systems, not as a simple system, and we compared with a couple of examples. And then I discussed the effectiveness of solutions. When you are increasing the robustness, then the complexity will be increased and solution effectiveness will be affected there by the complexity. I took an example of rather than having a couple of devices for the redundancy or the robustness, if you increase up to the 3 or 4 devices, then your complexity will be increased and number of failure points will be increased. And even though you try to implement the robustness by increasing number of redundant devices, then it is increasing the complexity, and then the solution effectiveness will stay as same or decline based on this particular graph as well. Then I explain you the unstructured network and the policies in the industry. If it works, don't touch it is not the way to go forward. And then discussed on the different planes, control plane, data plane, and forwarding plane. Forwarding plane mainly responsible with the hardware circuits or ASICs, and control plane mainly responsible for the routing and the controlling functions such as address ARP, which is mapping the MAC address to IP address, and the routing protocol, and MAC learning process, which is on the switches. How I think the design courses on the first semester have covered on the details of this what's called the MAC address filtering on the switches and the difference between hub and switch. So I'll be not explaining the details on the MAC learning. If you have questions, you may ask at any time. And then I explain you the separation of data plane and control plane, and discussed on the software-defined networking based on the centralized controller and open flow protocols. And this is the software-defined networking architecture and the different layers of application control and infrastructure layers. And we discussed on the network function virtualization, which is the hardware appliances becoming the software applications, which you can run on the VM or any appliance as well. And we discussed on the failure, network failures and the downtime and uptime on all these details, 4.9, 5.9s, and we got an indication of what 4.9s or 5.9s mean in terms of downtime per year, month, and the week. and then discussed on the potential network failure and the behaviors or the partial failures as well. Then hardware failures discussed in detail and the software-based failures as well. The reference book also included here. Then the fourth session, which is the last session on 28th, it is we are on the performance degradation and failures with the performance matrices discussed in the detail, and the network failure included with the network performance metrics, and we discussed 6 of them because we have limited amount of time, and I explained bandwidth, latency, throughput, packet loss, jitter, and error rate as the metrics in there. And then I went into the detail of taking let me go back to the bandwidth. Bandwidth I explained as the maximum rate which data can be transferred over the network, which is a theoretical limit. Then there's something called throughput, that is the practical limit. Even though you have a theoretical limit, sometimes you can't go beyond a certain point. And latency we discussed in details as well. Then the packet losses and jitter, which is a variation of delay, and I explained the iPerf as one of the tools you can run and test to measure this thing what's called jitter. Most of the applications can handle the latency, but it is difficult to handle or not intended to handle jitter most of the time. So you need to careful or test your jitter before you deploy any latency or jitter sensitive real-time applications. So that's quite important to measure the jitter if you are doing a baseline before deploying an application. Just you can run this iPerf as a tool and measure your jitter, whether it is on the the acceptable level of jitter. In this particular case, jitter is less than 1 millisecond, which is mostly acceptable. In my opinion, usually I'm okay with any real-time application less than 1 millisecond of delay of a network, and you can measure the packet losses and the percentages as well. As you can see on the right-hand plane of the output, and you can find out the throughput and the transfer bytes within a second. So that's something you can get as a stat when you are running iPerf to measure jitter, in addition jitter and other variables here. So error rate is the last performance metric we discussed, which is a physical layer detection. We discussed on the cyclic redundancy check, CRC errors, which you can observe on the network interfaces by checking the interface counters of network devices, which you can find out whether you have any physical layer issues by identifying CRC or any other errors mentioned here. We discussed a bit of a few of the common test tools. Ping is most basic application which you test when you have the reachability with another machine with IP address configured. You are ping. You are running the ping application from source machine or source computer, and the remote computer will respond with the delay mentioned there as a time. In this particular case, 20 millisecond and 24 millisecond on first and second, and then third and fourth 20 milliseconds round trip delay between sender and receive source and destination, which means source sending a ICMP packet, then it's receiver getting it and returning it back, and you are getting two-way delay number as a output of which we call round trip delay, RTT. And here there is a summary stat as well with the average and min and max, which you can identify. You can ping any IP address or the DNS or URL. So that's most simple application everybody knows, I guess. And then we discussed on the trace route, which is another simple application available on almost all the operating systems, including Windows and Linux. And you are measuring the number of hops and the delay between each hop and the source computer. And until you reach the destination, it is sending by using a TTL expiry, which is a field on TCP/IP stack or TCP/IP packet. In this case, it's sending by ICMP. We'll be discussing the protocol stack to explain you today in terms of where the different protocol stays on the OSI layers that we can discuss in detail. So then I explain the output in terms of trace route. The trace earth is the command on Windows, but trace route is on Linux operating systems. And then I discussed another tool which if you want to measure the one-way delay or one-way latency, that's called one-way active measurement protocol, which is open source protocol developed by standardized under RFC 4656. So you can use this particular open source tool if you want to OW, if you want to measure the one-way delay only. And two-way delay has another tool, but it's again a standardized open source tool with RFC 5357. So just wanted to highlight a few of the free open source tool. There are other tools as well, including iPerf, which you can measure. The iPerf has version 2 and 3. 3 has more features. There are many tools like NutTCP, which we will not be covered here, but I checked with your course coordination team in terms of your instructor level practicals. So they will come back to me on the next week, and they will share the schedule after they finalize with the instructor. Most probably I will be giving a lab sheet with these tools and how they are used in terms of the activities. So that I can update you on the next week in terms of since we have enough time to do the practicals, because course goes ahead, this particular semester goes ahead for many more weeks. So you have enough time to have these practical sessions on these tools, as well as some of the trace, the packet tracer lab exercises as well. Okay, then after we discussed on the performance metrics, one of the metrics I took specially, which is the latency, and explain you how to optimize the latency by just for an example, because we are unable to cover all 6 metrics we discussed previously. I just selected one and explain you as an example how to optimize end-to-end latency. Usually latency, if you consider a latency, end-to-end latency from sender to receiver, you can consider having application latency if there is an application. Then the network stack latency, usually on the TCP/IP delay and the kernel kernel network stack delay has roughly about 10 microseconds, which we can optimize by low latency tuning. And then there is a serialization and all the delays induced by the network card and it driver stack. And then after it serializes the converting bytes to bits, it's sending to the first network device, which we call first of device, and or the access switch or something. There are several namings you can put on the first device. Then it will be sending the end of row switches or the core switches, then the top of rack switches on the remote side, and again on the network card and the network driver delay on the remote side, again on the network stack delay on the operating system, and the application delay, which is variable based on how the developers programmed or developed your application. It's variable. We need to get each and every application latency separately because we have limit. We can't generalize that. The others can be generalized because we have mostly common operating systems, Windows or any Linux, and we have the typical latencies published on the switches and their data sheets, and the network cards are also again published with the vendor data sheets for the generic latency assumptions. So end-to-end latency should be optimized, not only the network devices, but you need to optimize on the OS stack plus the network card and driver stack as well, if you want a real reduction of latency for the applications. And I divided network latency for the 5 sections: the distance delay, serialization delay, queue delay, forwarding delay, and the protocol delay. Distance delay means usually speed of light, and the distance, the maximum speed you can think right now is the speed of light, and the electromagnetic signals having different speed on the fiber or copper cables, and by using satellite, which is the medium is air, and each having different distance. If you, distance matter in terms of delay or the physical geographical distance, as well as the medium, the signal, electromagnetic signal traveling on. So distance delay, it is we can fine tune that very much. It is difficult to fine tune because the maximum speed you can't go beyond speed of light, even though there are the quantum entanglement and all those research going. Still, practical limitation is this speed of light, and the physical distance matter. For an example, if you are communicating between Colombo and Kandy, and if you compare with Colombo and New York, that's you can see the difference in terms of delay when you are using real-time applications. So distance matter, both physical distance plus the speed of the medium matter in the distance delay. And the serialization delay, when you are converting bytes to bits, usually within your computer or the servers, you are running within that context. You are running on the bytes. Then your network card converting bytes to bits before it's transmitting to the network. So that is called serialization delay. It's taking time. If you are, I explained you that if you are increasing the bandwidth, it's providing the parallel processing or parallel serialization. So just increasing the bandwidth, you can get reduce the latency. For an example, 1 gig Ethernet serialization delay for 1500 MTU bytes packets, it's usually 12 microseconds. But if you go to the 10 gigabit Ethernet, it's reduced up to the 1.2 microseconds. It's 10 times of reduction. So just it's the idea here is, if you increase the bandwidth, definitely it enable the reduction of serialization delay as well, and not only increasing the bandwidth of the pipe, which is you can send more packets, but under the reduced latency as well. So that's an idea I wanted to give you on the serialization delay. Then the queue delay is the amount of time packet must spend in a network buffer waiting its turn to be transmitted, because there are several buffers induced stay, to stabilize the flow of packets. So usually buffers are on the switch ports and the operating systems, and everywhere buffers introduced on to manage the speed mismatch, as well as streamline the packet transmission process. So buffer, when something gets into the buffer, it's adding the latency. So you can adjust the buffer sizes based on your real requirement rather than having heavy buffer sizes induced. And then forwarding delay is the fourth one. Amount of time it's take network devices to process the frame and packet by performing destination address, because the switches usually sending packets by checking its destination MAC address and some other fields, but there are switches which we call store and forward, and it's waiting. Those switches are waiting entire packets get into the buffer, switch buffers, and then forward. But the cut-through switches, if you want to reduce the latency by using network devices, then you can select cut-through switches, which doesn't wait until the entire packets or frame gets into the switch buffers. And it's immediately forwarding after checking the destination MAC address. That's for the just for the forwarding functions. So it's almost immediately wire speed forwarding by the switches. So forwarding delay can be addressed by selecting the store and forward or cut through switching on the switch level. Then the fifth one is protocol delay. The protocol delay is usually can be handled in a different way, because most of the time we are depending on the TCP/IP stack. TCP/IP stack developed more than 50 years back. At that time, there were no real concerns or addressing on the latency issues. So those TCP/IP protocols are mostly not developed considering the latencies. So now there are ways to optimize TCP/IP as well as bypass the kernel bypass, which is to bypass the TCP/IP stack, which is directly communicating with the user space rather than going through the kernel space, so that we discussed on the last week. So there are several methods to reduce the protocol delay as well. So these are the five main contributors of network latency, and you can optimize each and every one based on your understanding. Distance delay, I'm going back to the distance delay, can be address on your data centers. If you host something on the remote data center or the cloud environment, usually when you are if your cloud data center not residing in your own country or own geographic area, you will be getting higher distance delay on those applications hosted remotely. If you have a local hosting or local data center, then distance delay will be much lower, because it's within your own enterprise premise, or it's within your own geographic area. So those are the and again, for the data centers, which for the lower latency applications, ultra low latency applications are running on, you can reduce the cable length as well. If you're connecting servers, you don't need to connect by using 5-meter cables. You can reduce up to the minimum level of cable distance, which can be 1 meter or less. So those delays can be optimized by using several techniques or best practices in the market or the industry. All right, we discussed the option of serialization delay and why the different aspect thereby comparing the different bandwidth from 10 Mbps up to the 100 gigabit Ethernet. And I mentioned you that from 1 gigabit or 10 gigabit Ethernet onwards, you will be getting lesser overhead on the Ethernet, which is previous encoding method, having 8 bytes of traffic and 2 bytes of overhead. If you are sending a packet, now it's 64/66, which means 64. If you are sending 64 bytes, then it's only having 2 bytes of overhead, and compared to the percentages, you are having lesser overhead in there with the latest 10 gigabit Ethernet standard. It's not just upgrade of 10 times. And again, there are things like physical layer bandwidth and data length layer bandwidth. On the 10 gigabit Ethernet and 100 gigabit Ethernet initially were having designed for the 100, 10 and 100 are representing physical layer bandwidth, and logical layer, which is data link layer bandwidth, is much lesser. But 1 gigabit Ethernet onwards, the data link layer bandwidth was the target, and you are getting more bandwidth, overall bandwidth, due to this change on the standardization approach. And this IFG means interframe gaps. When you are sending bytes, always machines maintaining a gap between two packets, which is 12 bytes by standard. So that's represented here based on the standardization approach. And then I discussed on the different frame sizes, and the minimum frame size usually you can have on Ethernet is 72 bytes, and the maximum or MTU usually defined as 1500 bytes. You can see maximum transfer unit by MTU on any operating system or any switch. Usually by default 1500 is the MTU, and the minimum you can send is 72 bytes. There is a reason for this, because Ethernet frame definitions having its own control or control overhead. So it's at least taking 64, or in this case, it's additionally 72 bytes overhead is there. If you are sending a data packet without any data, or without just for the control without any data, which means 0 bytes of data included there, the frames taking 72 bytes of overhead, so which is the minimum size of frame. So we can measure the serialization delay. If you have 72 bytes, it's taking 84 microseconds. I explained to you that microsecond is 10 to the minus 6 from a second. The 10 to the minus 3 is the millisecond, 10 to the minus 6 is the microsecond, then 10 to the minus 9 is the nanosecond, 10 to the minus 12 is the picosecond. Right now we'll be discussing on, I think the after today we are going we are covering entire network troubleshooting fundamentals. Then we will be on the next weeks, we will be discussing on this time stamping and time synchronization as one of the lessons. We can discuss on details of the time synchronization and time stamping in there based on the different precisions. In this case, serialization we measured by using microseconds. For you can see that if you increase the bandwidth or increase the Ethernet bandwidth, you can see that serialization delay reduced tremendously, and compare with the minimum frame size as well as MTU size, which is 1500 bytes. So you can see that serialization tremendously reduced when you have larger pipes. There is something called jumbo frames. These days for the data centers, you can go up to the 9,000 of frame sizes for the data center switches and the data center servers as well. But for usual enterprise machines or servers, the frame size or maximum transfer unit MTU size usually on 1500. But there are data center, since we are discussing data center networking as well in this these sessions, you can now see that switches and the servers with the MTU size adjusted, especially on the VM and cloud environments, 9,000 bytes frame sizes, and you can see the serialization advantage there by increasing the bandwidth, clearly comparing the numbers. The 72, if you have 1 gigabit Ethernet, the serialization delay will be 72 microseconds, but it's less than 1 microseconds if you have 100 gig Ethernet implemented. And I further explain you the details on the Ethernet roadmap. In 1980s, we were having 10 Mbps Ethernet, then 1990s upgraded to 100 Mbps. And before 2000, there is 1 gigabit Ethernet. Then after 2000, 10 gigabit Ethernet. Suddenly on 2010, there is 40 gigabit Ethernet and 100 gigabit Ethernet. Recently, there are several standard before 2020, which is 50 gigabit, 200 gigabit Ethernet, and all those are there. Network cards and switches are there in the market right now with all these new standards. And you can see that 25 gigabit Ethernet, most of the time, the current day data centers are not 10 gigabit Ethernet, but 25 gigabit Ethernet switches, and the network cards are there. And the uplinks usually taking 100 gig or 200 gig for the network devices, and the servers having network cards with the 10/25 gig with the backward compatibility. And this 5 gig and 2.5 gig for the home-based devices, home networking. Usually you can see that network adapters or the USB-C adapters are there. Let me check. I have one. So you can see here there are 2.5G 2.5G marked here. This has the RJ45 one side, and another side is USB-C. There are 5 gig adapters as well. Even the home base switches and the routers now having 2.5 gig Ethernet. This is mainly the 5 gig and 2.5 gig mainly developed because there are enterprises having old cabling systems which are mainly wired for 1 gigabit Ethernet, but recently those cables identified and tested to run on 2.5 gig and 5 gigabit Ethernet. Usually the cabling takes they require more budget to upgrade and require drilling and breaking of the walls sometimes, or cabling with the casings. So it's difficult, and that's why the people introduce, or standardization authorities, IEEE introduced 5 gig and 2.5 gig. Now it's quite popular among the home networking users with the new devices beyond 1 gigabit Ethernet. So already there are 800 gigabit Ethernet on 2025. Now the NVIDIA having network cards with 800 gig and the switches from Arista and Cisco for the 800 gig. And soon there will be 1.6 gig Ethernet, especially these the new standardization speed up with the AI and data science workload requirements. So these are there in the market right now with the 800 gig. Most within this year, I think you can see the 1.6 terabit Ethernet as well. All right, in terms of latency, end-to-end latency, I explain you further how to optimize, reduce the kernel latency, reduce the serialization delay by selecting network cards, which is ultra-low latency network card or smart NICs, and the switches with the cut-through feature rather than store and forward. And you can really get the end-to-end delay less than 10 microseconds these days. This slide is somewhat old, I guess. So now you can get less than 6 microseconds end-to-end delay by optimizing with the latest switches, network cards, and the kernel network stack optimizations for the end-to-end latency for the one-way. And this is store and forward and was cut through latency explanation. I explain you that the store and forward waits until entire packets get into the switch buffer. Cut through only reading the destination MAC address and forwarding it based on the MAC address table. It doesn't wait until entire packets get into the switch buffers. So it's providing definitely the predictable latency and the latency advantage. But there is a slight disadvantage as well in terms of if you implement any security policies on your switches or the network devices, then it is difficult to implement that by using the cut-through switches, because you need to get entire packet into the buffers if you are forwarding based or forwarding by policy-based routing or policy-based switching, or implement any security policies there. So there are pros and cons between store and forward and cut-through. Mainly cut-through preferred on the latency is a main requirement. Then I wanted to explain you that you can bypass the kernels or network stack to reduce the latency, because TCP/IP stack developed not in the latency in mind on 50 years back. Now there are the proprietary methods such as all these are open source drivers. But still you need smart NIC hardware to be run on. You can directly, your applications are mostly generally hosted on user space, so applications can directly talk to the network card without going through the kernel stack or the TCP/IP stack, and directly communicate with by omitting the latency induced there. This is an example of directly communicating applications through the open on-load driver with the network card there, which is mostly the AMD Solarflare network card, using this approach to bypass the kernel. This is one of the approaches which you can use to reduce the latency in terms of bypassing the cable kernel space. And this is another example, which is TCP offloading. You can offload certain TCP functions from the operating system software to the hardware, which is on the I/O network card adapter, especially with the modern network smart NICs, smart network interface cards. And these techniques are available. There is something called remote direct memory access, RDMA protocol is there for the low latency environments, especially on the AI workloads. These technologies are heavily used on the ultra low latency. One of the functions which RDMA is doing, it's offloading the TCP/IP stack or the network OS network stack to the hardware or the network interface card. And there are other ways, not only offloading TCP/IP, it's possible to offload several OS buffers and the driver buffers and to the hardware network interface card, and directly communicating applications by using application buffer to the adapter buffer rather than going through the operating system and adding delays. This RDMA, which means Remote Direct Memory Access method, is having a couple of advantages, which means offloading the TCP IP stack or the network stack from the kernel, OS kernel, then offloading the adapter buffers or the OS buffers and driver buffers to the network hardware, network interface hardware. So this is one of the approaches to bypass the kernel. The previous one was on the kernel bypass driver can be used, which is mostly the proprietary or the open source. And the RDMA providing a couple of advantages, as I explained before. And there is another optimization, which we call traditional server IO architecture, usually are based on von Neumann architecture, what we call, which is developed by the mathematician or the computer scientist on the last century. So the von Neumann having several issues in terms of its functionality. Usually when packets arise to the network card, it's usually copied to the CPU registers, then coming back to the application, copying back to the application memory. Then another copy goes to the IO memory pool, and then IO memory pool having communication with the application memory. There are the multiple copies within the same CPU architecture or same within the machine infrastructure. But this can be optimized. This has optimized by using RDMA protocols, the kernel bypass mechanisms. Now the bypass capable smart NICs, so network card adapters are quite capable of directly copying only to the application memory or the rather than going through the kernel level and or multiple copies on the CPU registers and memories or IO memory pools. So these technological the zero copy architecture, which is available, and now those techniques are available on the server infrastructure, and you can get those network cards with the zero copy capability, and implementations are there if you need to implement something on the core banking or the stock exchanges or any ultra low latency application. If you are deploying these technologies, can be used to reduce the latency or minimize the delay. And there's another protocol which is based on the RDMA, what we discussed, which is mainly developed for the high performance computing plus the ultra low latency. That's called InfiniBand. Another, it's built again Ethernet plus TCP/IP. The stack developed from the physical layer to the application layer. The standardization authority is IBTA, InfiniBand Trade Association, software stack maintained by Open Fabrics Alliance. And I put up a references if you are interested of knowing the details of these high performance computing and the ultra low latency implementations to reduce the latency. And this is the packet format, which is different from the Ethernet frame or the TCP/IP frame, TCP/IP packet, just for your reference. And previously we compared different bandwidths or the Ethernet roadmap. Now this InfiniBand roadmap also the very well developed, and even though Ethernet was having 1G some time back, these guys were having 100 gigs, 56, the 40 gig, 56 gig, and having the fastest speeds at the time, and mostly high performance computing clusters, and have been using this InfiniBand for scientific computing and the modern day AI and data science workloads. And this is a kind of a comparison. You can get the latency between different technologies from 1G marked here, the highest latency on the 1G Ethernet. 10G Ethernet having much better latency marked by green lines. And the RDMA is the lowest based on the InfiniBand. And there is something called IPOIB, which means InfiniBand can be run on the IP, but still you are getting the protocol overhead and not much optimized there. But it's enabling the compatibility. But if you use RDMA with the InfiniBand, you are getting the best latency here, less than 20 microseconds. It is now much lesser than that. This slide is somewhat older. And CP is a session description protocol, which is another implementation of InfiniBand. And these are the RTT, round trip time latency. If you want to compare, you can see the drastic reduction of latency by selecting a protocol and selecting the bandwidth in terms of comparison here on the 1G versus 10G. And this is the software stack by Open Fabrics to support InfiniBand and RDMA infrastructure. And just putting your reference, we will be not testing these on your final examinations or assignments. And InfiniBand is a fabric technology. You need to have all the equipments and network cards running on the InfiniBand. If you are running with the InfiniBand, it's a clustering technology to enable faster communication between servers. But there is an issue because most of the networks in the world are based on Ethernet and as well as TCP/IP protocol stack. So people wanted to use the physical layer or the Ethernet as the bottom layer protocol and need to run other InfiniBand layers on top of Ethernet. So that's the InfiniBand Trade Association announced a protocol named Rocky, which we call RDMA over Converged Ethernet, which is available, famously used in most of the data centers these days for the ultra low latency and high performance computing. First version of Rocky is running on top of Ethernet, which is on the link layer, the second layer of operating OSI model, and all the layer 3 and above upper layer protocols are running on the InfiniBand stack or the sub layers. Then people wanted to have not limiting up to the Ethernet. Most of the network engineers are compatible with the TCP/IP stack, so they wanted to have TCP/IP or Internet protocol at the third layer and the UDP for the multicasting. Then the Rocky version 2, which means RDMA over Converged Ethernet version 2 implemented, and this standardization is there. Now modern day switches and the network cards the low latency network cards are supporting this Rocky protocol. If you're purchasing switches or the network cards for your data center, probably if you're planning to deploy low latency applications or enable high performance computing, you can think of checking the spec of your network card. And the switches, most of the modern day cut through switches and the smart NICs are supporting Ethernet. Smart NICs are supporting this RDMA or Converged Ethernet protocol. So you can think of when you're designing network, you can think of considering these modern day technologies to reduce the latency. This is just for your reference. I'm putting here the Rocky version 1 and version 2, the packet size, the packet structures. So you can see that Ethernet layer 2 header is there on the Rocky version 1, and additionally you can see that IP header included with a UDP header on the layer 3 before the layer 4 header and the InfiniBand payloads on the trailers. So that's in terms of I just wanted to highlight that how far we can go in terms of one metric which we selected, the latency, and how we can improve that by optimization with the modern day technologies and the different techniques to reduce the end-to-end latency, which is the selected metric as an example for you to show the how far we can optimize that. The similarly other metrics you can think of optimizing, and several ways are there. This is just an example for your academic purpose. So to get understanding in terms of your planning data centers as well as your end-to-end reducing the jitter and latency when you are planning to design a network. Okay, that's about the recap. I took time because I just wanted to establish the fundamentals here. That today is the last day in terms of fundamentals. We'll be moving from the next week onwards for the emerging technologies plus the best practices and most of the industrial practices in terms of network troubleshooting. All right, these were the reference books as I mentioned before. So let's start on today. This session 5. We have covered almost all on the network troubleshooting fundamentals. This is the last section in terms of troubleshooting fundamentals. On the next section, which is after 10:45, we'll be discussing failure modeling. Let's discuss on the network troubleshooting fundamentals based on scaling, aggregation, reliability, resiliency, and redundancy. These 5 aspects are important to understand, especially when you are designing or running troubleshooting a network. These aspects are important in terms of coming into conclusions based on your troubleshooting and general understanding. Some of these ideas may have covered on your first semester network design course, but we are covering here based on the network troubleshooting aspect with the deep dive in the context. Okay, do you have any, before I start the session, do you have any concerns on any questions in terms of what we have learned on the last couple of weeks? You can always ask questions by unmuting, or you can raise your hand by Zoom applications, or just type your question on the chat, individually or public chat. Okay, let's start on the session. If you have questions, you may ask at any time. Network design goals and troubleshooting techniques is the next topic in term before we go ahead on the scaling and aggregation, reliability and resiliency and redundancy. When you first consider adding a designing or redesigning a network, whether large or small, what are the first things you think about? So if you are designing a network, the question here, if you have a task to design or redesign a network, whether it is large or small, what are the first things you think about in terms of the aspect? So mostly, then there is another question on this. Do you begin by thinking about the types of links, which means are you planning to use 1 gig, 10 gig, or 100 gig, or the types of routers, whether you are going with the Cisco or Arista or Juniper routers you would like to use, or even the routing protocol which you are interested, which is routing RIP, BGP, or OSPF. There are several dynamic routing protocols which you may have learned on the design course. So those are the ideas may automatically come, but those are the ideas. It should not come as a first. It can be considered at later stage. Because you should think about what you would like your network to do, because you should, as we discussed initially on the top-down approach, for the designing or redesigning, it's required to consider your initially in terms of the applications you are running. What are the business applications you are planning to run on your network? Then design your network based on your application requirements is the best way to move forward, rather than the bottom up. Mostly you should consider the bottom up is if you are thinking of what are the cable or the link types, if you are thinking of router models, if you are thinking of routing protocols, then it's a kind of you are thinking by the bottom layers of OSI model protocols or the requirements. But you should start from the application layer or the applications you are planning to run for your business to function or business to benefit. Then you can plan based on the application requirements. That's people call usually application-centric infrastructure planning, because that's the main function of your business. You're doing business to have profits or the profits or do a business function. Then it should be mapped with your exact IT IT applications. Then those applications catering for the business functionality. So you should start from the top, not from the bottom or the middle layers. And this particular diagram or particular picture showing that the number of racks, switches, and the routers implemented there, some cables connected, and there is a network rack, and you have command line protocol, which is for a router. You are considering routing protocol, in this case BGP protocol implemented, then several routes are there. This is a kind of a view for a technician to have. But if you are planning to have network or designing a network, you need to think of a think from top to bottom rather than bottom to top, or the thinking about thinking based on the middle layers. All right, any questions you may ask? Network design goals and troubleshooting techniques can have a relation. There is a clear relationship, because if you are designing a network which is based on the goals of your application requirements, and your troubleshooting or the ops team should have a way to troubleshoot if there are issues. If there is an issue, then it should be easier to troubleshoot and fix it. That should be in mind when you are designing the network. That can be one of the goal which you can recover. I think your first semester covered on MTTR and all those aspects. If there is an issue, you need to recover it faster, reducing the unavailable time or downtime. So it must be a goal when you are designing a network. It's quite important. In terms of there's several aspects you can think of. What should the characteristics of the network? What are the applications you are running? Are you running low latency application, or are you running application which are real time, which is for the voice over IP, and a kind of a application requirement or characteristics need to be get understanding, because the different application have different characteristics. For an example, voiceover, if we have a requirement for voice over IP, that is comes under the real-time communication, which require when you are taking a call through the network, the remote person need to hear it real time, without echo, without disruption, or without breaking the voice. So you should consider the latency aspect as well as jitter aspect in this particular voice over IP application. But yeah, if you are doing, you can you can drop some amount of packets, but still you can continue the voice conversation. But in terms of if you are planning this for the file trans applications, you can't lose even a bit, because you need to transfer entire bytes, all the bytes from one place to another place when you are transferring files. you can you don't need low latency tuning for the file transfers. You can, if it is transferred within a sufficient time as expected. So you don't need real-time communication for the file transfer. So the file transfer application has different characteristic compared to the real-time applications such as voice over IP or video over IP. So what are the goals of the network design? The network design, you can define several. You may have a 24/7 application running, like online banking application, or your enterprises have running application which is supporting the sales of 24/7. Or there may be some applications running 8/5 only with the weekdays for 8 hours running. So you can think of the uptime and goals of your network design based on the application requirement again. How can the network carry traffic so that it best serves the business needs? So you need to consider the business requirement in terms of mapping your network design. For an example, let's say your business required to scale up to the certain level, or future network within next year, within 2 years we will be scaling it to up to a certain level. Then those need to be considered when you are designing a network, and the traffic will be increased with the several new application introductions and the scaling client base. Those factors need to be considered in terms of scaling as well as business requirements over the years. Then network users see the network as bundle of applications. Usually the users are not concerned very much about the wires and the network devices or the protocols. They just want to use the application by using the network. So that's the real requirement. So that need to be understood, because if you are taking a user survey or user requirement analysis, then they don't care whether you are using the wires or fiber connections, protocols or routers or the switches, where those are specific in your mind. The user require mainly to the transfer, run the bundle of applications smoothly without much of a disruption, or up to a certain service level agreement of the performance. What are the capabilities will a network need if it is going to carry traffic to support applications? So as I previously explained, the different characteristics and the application must have different capabilities if it is going to carry traffic to support applications. Applications may have different components. Some of the applications having the multitasking functions within that, and some of the applications need to host it on-prem, some of them are on the cloud support, some of them are on the hybrid. You need to consider all the capabilities of the applications as well. So basically, I just want to highlight by this slide, if you are designing, troubleshooting, then you need to consider planning for troubleshooting. You need to consider several aspects, mainly targeting the application aspects. The goal, let's discuss detail in terms of goals common to the most network designs that we can get as an abstract. The network should stay up all the time. Mostly expectation from your business, because business is heavily dependent on your network and the applications. The applications need to up and running, and therefore you should have up and running network, which should be reliable, I guess. And network should reliably deliver the packets. You should have the network has the capability to deliver the packets reliably, because you can't expect your network to run well on sometimes, but not all the times. So you need to build your network based on the reliable communication, not based on the fragileness, as we discussed on the risk approaches, re- exposure of the risk. Within reasonable delay and jitter. In this case, you should consider the characteristics such as the metrics we discussed on the last lesson should be addressed based on the application characteristic from one host to another host. Even before you hand over the network to application users or the application deployment personnel, you can consider running certain baseline tools to check the readiness of your network for the applications. So for an example, previously we discussed iPerf as a baseline tool, which you can measure the jitter, and there are some tools to measure the delay as well. Those tools can be used to benchmark or the baseline network, measure the baseline of your network, and then if those are fine, then you can hand over to the application team. Otherwise, you need to rectify the issue, and then once you get the proper baseline numbers or expected numbers, then only you can hand over the application team to deploy the applications on the network. Then the troubleshooting should be fairly easy, because if you build a network which is difficult to troubleshoot, if something happen suddenly for the network, then it will take many time to fix it, and it enable more downtime, which may not be expected by your business team or the management. So network should be secure. Since we are doing masters of cybersecurity, the security aspect is important for the network, because previously, as I mentioned before, even TCP/IP stack developed 50 years back, the latency was not in mind, and further security also not integrated there in the TCP/IP stack. So therefore you need to consider additional security if you are using traditional protocols. So how to secure your network by introducing the devices such as firewalls, or the several other secure devices, or security implementation methods, or the best practices can be used to secure your networks. And then you should have some sort of monitoring facility, because even you don't need to wait until something happen and then troubleshoot. You can keep on monitoring the network based on its growth and scalability, and you can predict certain things by monitoring before the real downtime or performance degradation occurs. So if you keep on monitoring your network, then you can proactively address issues before even it's reflected on your network or applications. That is quite important on the network designing. And we will be discussing this monitoring aspect at the later of this course, especially on the Wireshark analysis, and all those lessons will be there the later part of this particular course. The network should be easily modifiable. If there is a demand for the application, demand for bandwidth, or demand for scalability, then you should have the architecture which is scalable and easily modifiable, which is based on the design patterns which we are learning, which usually learning in the network design courses, as well as we can consider it here as a requirement when you troubleshoot something and you need a fix. Then if it is easily modifiable, then easy to implement the fix. And that is quite important in terms of network growth aspects, either by traffic increase or by application demands. with the new application introductions. Any questions before we move to the next one? Okay, let's discuss on the underlying fundamental goals in terms of reliability and resiliency. The network must be reliable and resilient. These are two different terms, but there are overlaps as well. The packet must be reliably delivered with fairly consistent level travel times from source to destination, from the machine A to machine B. It should be reliably delivered because you can't have packet drops between there if the application is sensitive to the packet drops, and you need to have reliable network because if there are packet losses or the sudden high jitters, then you can assume that network is not reliable. And you should have consistent travel time, because if the travel times varies between one packet to another, that's we call jitter. It is not tolerant to most of the applications, so application performance will be heavily impacted. And major changes in the topology and the intentional if there is a major change in the topology, there should be automatic recovery, even though it is intentional or unintentional. It should not impact the network performance, even though based on your application requirements. So network must be reliable. Reliable means you can have the trust on your network. This will, if I send packet from A to B, it will be delivered within fair amount of time, and it is resilient enough. If something happen, it will automatically recover back to the normal level, which we call resilient, or sometimes we call robustness, which is coming back to the previous working state, as we learn on the network risk management. Then another term is the network must be manageable, which means you need to be able to find and correct the problems quickly within the limited time. You should have right people with the experience on troubleshooting and correcting the issue, and the right tools with them to analyze something like Wireshark or the network monitoring tools. So analyzing tools must be there, and the probes must be there to capture the packets, and the historical data should be there. And that's the idea behind network must be manageable. The third bullet point is the network must be scalable. If there is a demand growth in your network, you should have the scalability to support your growth of application traffic or the introduction of new application traffic, there, rather than having the huge forklift upgrade. But there may be situations after certain many years, your architecture need to be, or you need to retire your network and build a network based on the modern architecture, because network devices plus the methods will be obsolete after certain period of time, or the vendors may announce end of life for the equipments. Then you can consider upgrading your network or building your network with sometimes retiring the entire network which you built 10 years back. So those are the aspects in terms of network design. Goals as fundamentals. And let's discuss difference between reliability, redundancy, resiliency, and redundancy. Reliability and resiliency often go hand in hand. A resilient network tends to provide a more reliable and stable platform for the applications, and close examination of reliable network tends to uncover good amount of resiliency. These two terms are mostly go together, but resilient network tends to provide more reliable and stable. You can trust. Resiliency means you can trust on your network. The resiliency means your network, if something goes wrong in your network, it will recover fast, and it is difficult to make it fragile because you implemented or considered your design as a resilience design to come back on any failures by introducing several network recovery methods. And the reliability, your trust on your network, which is reliably communicating, it's a kind of assurance your network running as expected. So those are two terms. Do not mistake resiliency for redundancy. Redundancy is something else because people think the resilient means you are putting couple of devices for the redundancy. No, sometimes it's beyond the redundancy is one of the approaches to address the resiliency, but resiliency is not equal to redundancy. The redundancy is one of the approaches you can use to maintain the redundancy or enable the redundancy. Although redundancy is one good way to provide resilience in some situations, simply adding redundancy to network does not always increase resiliency. We discussed this matter on the network complexity as well. Having couple of devices for the redundancy. If one device fails, the other device can take over the functionality. But if you implement the over redundancy, which means introducing third device rather than having couple of devices, you are increasing the complexity, and there will be more failure. The complexity increase can make more situations which are sometimes unintended in terms of edge, considering those as edge situations. So more failure points will be there since you have 3 devices rather than having 2 devices. So this over redundancy is a kind of thing you need to avoid. So sufficient redundancy implementation is quite important based on your business requirements rather than one thing is it's increasing the complexity and reduce your downtime and reduce your effectiveness of solutions. You don't need to implement over redundancy in your network by the sake of having more devices than you absolutely require. Any questions on these differences of reliability, resiliency, or redundancy? Okay, there will be questions on your assignments plus the final examinations, mostly these 3 areas. A reliable network delivers virtually every packet accepted by the network to the right destination within the reasonable amount. So again, explaining the reliability in detail. Expectation is on a reliable network, the packet from A to B will be delivered within a reasonable amount of time. Not every packet that is transmitted by devices attached to the network will be accepted for the delivery. But still there are several rules, because even the network accepted a packet, it doesn't mean that packet will be delivered definitely, even though it's accepted for the delivery. Then not every packet that is accepted by network going to be delivered. So that is another aspect. Even though every packet packet accepted, that doesn't mean all the network is delivering all the accepted packet. Accepted packet need to be delivered quickly. Accepted packet need to be delivered consistently, not randomly. So that's the main 4 ideas. What I mean is on the first bullet point, not every packet that is transmitted by devices attached to the network will be accepted for the delivery, because there are packets you shouldn't be delivered to to the each and every host. For an example, we'll be discussing the multicast on one of the lessons later. When you are sending packets to multicast, it doesn't mean you are delivering it to the everybody in the network, every host in the network. You are delivering only the requested receivers. And again, the second bullet point, not every packet that is accepted by the network is going to be delivered. Sometimes packet is sent by the sender, but there will be implementation like quality of service, QoS. If you have implemented and assigned priorities for your different applications, only prioritized or packets will be delivered. The remaining packets can be, if there are congestions, there will be drops. So based on your quality of service policy, there will be a low priority packets which can be dropped based on the congested situations. Accepted packets need to be delivered quickly. That is acceptable. You need to build as fast as possible. That's a common accent, rather than delaying the packets even if you have bandwidth or no congestions. Accepted packets need to be delivered consistently. It should be delivered consistently without having high jitter or higher variance. So those are the fundamentals of the network reliability. Still, you based on the reliability aspect of the network. Any questions? Okay, this is one of the example of the reliable delivery of the packets. The application usually sending this, there is a source and there is a destination machine, and the two routers in between connected by network segments or cables and the switches. The application builds packet at a specific interval, sending packets with a right right interframe gaps. There are gaps between the packet, which is consistent, and we have been discussing this interframe gap concept on the serialization delay lesson. You can see that interframe gap is usually 12 bytes. So now the sender is sending with the right gaps. Application build packets and specific intervals. The sending network stack and media layer cause packets to. Now you are sending it to the switch, but switches having buffers, sometimes getting the gaps between the packets may vary by adding the switches there. Then on the second device, which is the router, and further jitter and delay are there. You can see the difference between some of became shorter, some of became longer between the different packets. And then you are going on the second router, and you can see the more variation there, based difference between the packet or the delay between the packets. There are the heavy variations in this case. Now the receivers getting with the large variations between the packets, and it should reorder or wait for some time to wait for some time based on the protocol to make it more serialized or make it similar to what's sent from the source side. So there should be mechanisms to handle the jitter based on this situation. So application receives the packet, they're somewhat clumped, and some are lost, and there is a variable amount of time between each packet. There can be losses on the switch buffers or the router buffers. So if there are lost packets, you can use protocol like TCP to request the packet based on the TCP timers. But there are protocols like UDP, which is not reliable, as its name, unreliable datagram protocol. If you are using that, you can't request protocol, request the missing packets. There is no mechanism. But TCP transmission control protocol have those mechanisms. So you need to, if you need a reliable communication, then you can consider selecting your protocol like TCP or UDP if you don't expect, excuse me, if you don't expect reliability as a matter. Like in the case of multicasting, usually you can use UDP protocol. In this case, you can see that the variation of delay between the packets, and some packets may be lost. So reliability need to be addressed by the protocol level and your design level, as well as to avoid enable the reliability, you need to select careful on the selecting protocols for the reliability requirements, and the packet losses need to be addressed, and jitter should be minimized, and all those aspects need to be addressed in the reliability, considering this specific use case scenario or the example. And there are other things like host A to host B communication. This is another example to explain you in terms of host A, another use case. Host A to host B going through the router C and router D. This communication is there. Lightly loaded, moderated speed link. So it's lightly loaded, but not congested. Router E and router F is a high speed but heavily loaded trunk, because this is another network which is connect the router C from when you are sending traffic from A to B, you're first sending it to the C. Now router C has two paths to B. You can go through the router E or router D. So the router E is a part of another another network which is congested, but still high speed, not the moderate link as between C and D. So you can implement routing protocols, so the traffic engineering techniques to enable to select the best path based on the congestions and as well as the requirements there. Just leave it. Okay. So when you're planning your network, when you're designing the alternative routes or alternative network paths, you always need to have consideration on the selecting your best path in terms of enabling the redundancy. There are two redundant paths here. One path is through router D, and one path is through router E. So based on the dynamics of at the time of sending a packet need to be addressed based on the load and the capacity available, or it can be load balanced sometimes to sometimes to reduce the overloading of any of the single links. Most of the another aspect is most of the network engineers, when they think of network resiliency, automatically think of adding redundancy. The previously we discussed on the over redundancy rather than having enabling redundancy. I can show you a perfect show you the complexity there or the disadvantage there by implementing over redundancy. Just take this example. So now the first in the first case, now you have a couple of machines or the computers connecting to the router A and router B. Let's say you have a now if the link between router A and B disconnected or went down automatically, which is unintended, then you don't have any communication between A and B. So you can implement the redundancy by adding backup link. If the link between A and B failed, primary link between A and link failed, then you have a backup link marked by this dotted line. So it will automatically or manually you can shift the link to the backup link, and you have the communication after a small downtime. So having a backup link is better way to enable link redundancy. So, but you have a problem here. What now you have the link redundancy. If the link fail, you have a backup link. But what about if one of the routers fail, A or B fail, then still even the links are up and running. You have single point of failure at the router level, right? Router A or B fail, then you can't communicate even you have to have a backup link. So you can have something like this to enable the redundancy. By using the redundancy, adding couple of routers, you have another network segment having couple of routers. So you have the redundant networks there. Yeah, the primary network will be from A to B path. If one of the routers failed or one of the links fail, you can send traffic through the C and D. So that's the backup path. You are having couple of network devices and the two links. The links are there because you are enabling redundancy not only for the links, and the device redundancy also enabled on this structure. So that's how you enable you are avoiding the single point of failure. Has some but still it's having the issue of dual point of failure, which because if any two components fail, let's say some of the components are fine, let's say A and B fail, that's okay. What about if A and D fail at the same time? Then you can't still communicate. So still there are some dual point of failure situations, scenarios there, but single point of failure avoided in this design. But you can remove some dual point of failure by having couple of links, cross links between A and D and B and C. Because if let's say if B fail, primary link, primary traffic go through the A and B. If A fail, then you can go through the A and D fail, still you can go through the C and B path, which is the backup path, and as well as the C and B routers. Having cross backup connections, you can further get the further advantage and the resiliency by designing over that is adding considering some dual point reducing the dual point of failure situations. Right. So these are the ways to develop. What if you add the third link parallelly with another couple of routers, which is costing more, but still enabling more complexity, like dynamic routing protocol implementations, and the more failure points will be there. But if you are planning to reduce single point of failure and avoid much as possible dual point of failure, these are some of the examples you can consider in terms of planning for the redundancy rather than doing the over redundancy. You need to enable the redundancy with the purpose of enabling link redundancy or the device redundancy to avoid single point and sometimes occasionally dual point of failure. The most of the time, in the first hand, I consider only the first single point of failure. Then occasionally, if there is a business requirement only, I will be planning for the dual point of failure or further points of failure. So this is a kind of example you can go through. initially we had backup links to enable only the redundancy on the which is on the link redundancy, but still having single point of failure on the devices. Then we had couple of network segments with the redundant links and the redundant network devices. If one of the devices fail, or one of the links fail, it will switch over to the other network segment, but still having some dual point of failures like C and B failed, then there is no way to move traffic. So it avoided by having cross links between the 4 routers, and now you have you omitted several dual point of failure, and this is more resilient network than what we initially started on this. Okay, we discussed this on the complexity section as well. As the network grows, no matter how reliable the devices, you need more network devices and more components, and then automatically when your number of devices increase, there will be more failure points or more failures of devices. That's impacting overall downtime of your network. So you need to consider scaling as a barrier to your redundancy, your reliability and the resiliency of your network. So therefore, you need to have methods to scale your network while keeping the reliability and resiliency on acceptable levels. That's quite important. So scalability is not something simple, because you can't build a network by using the home network technologies for the enterprises. You can't build mission critical network like core banking systems by using usual enterprise networking techniques. So you need to consider scaling scaling plus the business requirements in terms of business demanding more traffic or the more applications. You need to careful on scaling with maintaining the redundant resiliency and reliability factors in there. So it's not something you can use to build large cloud network by using the enterprise techniques which you are using on the usual company network. So there are several aspects in terms of scaling. Even in the nature, you can see that there are limited number of animals which are having the large sizes, like the blue whale or the elephant in the land on the land are somewhat resilient, but they are not resilient as cats. You can see if something if elephant fall, usually it's fragile, but the cat fall from the 2-story building, still it survives with the minimal damage or no damage. Similarly, small networks are quite resilient. When you are scaling, you need to address that aspect and plan your network or design your network considering the scaling issues and the complexity. So that's quite important to get to understand. You can't use the same technologies you are using for the small networks for the large enterprises or the large cloud networks. Okay. This is the example of over redundancy. On the first diagram or top diagram, you have router connected by a link with another router. So you can see that you just have one link, and if the link is disconnected, then suddenly getting up, it will recover the convergence time since you have a couple of devices and converging the routing tables after the link pinging up. It's very minimal. I mean, If you increase number of routers, similarly connecting with this, then you can see that convergence time getting increased because the number of routers need to be communicate saying that this link has went down a few seconds before. Now it has recovered, and you have a path to this. The converging with other network devices taking time. It's not linear. It's taking time based on number of network routes in those devices. If you have more routes in these devices, take more routes to announce the recovery and update the routing tables. So similarly, you can compare that particular graph, a couple of routers interconnected by using two network links between that for the redundancy. If one link fail, the link will take over. Now you can see the second line of the graph. The convergence time will be further increased. You can compare the bottom graph with the top graph. It tremendously increasing with the introduction of couple of links if you have now based on the number of routes in those two routers. You can see the average as well. If one link is there, the convergence time going high with the two links. Similarly, if you have three redundant links, then you are getting further increased the convergence time. You can compare the graph, three graphs between that. Now it's further increased for the convergence time, because these routing tables need to be updated and communicated based on the link recovery and announced to other routers. See, we are just taking the example of between two routers interconnected. So increasing number of routes between just these two routers, the synchronization or the convergence increase heavily based on number of routers marked on the x-axis, which is 2000, 4000, 6000, 8000, and 10,000. So convergence time measured by milliseconds. The number of milliseconds, the 1000 millisecond is a second. The 2000 millisecond is 2 seconds. You can see how long it will taking while having routing table populated with number of routes here. So which means you can't increase the redundancy, increase the resiliency or increase the efficiency of synchronization or the routing table convergence by adding more links between routers, because it's over redundancy if you are increasing number of links between them. So it's quite important factor. If you are considering the scalability, you need to minimize number of links between that. You need to just keep absolute necessary redundancy implementation when you are scaling the network. It's mattered in terms of scalability. All right, just give me another 10 minutes so we can finish this off and start with the next lesson thereafter. So then we discuss on the redundancy, scalability, resiliency, and reliability. Those are some of the terms, but some are overlapping, but those are different terms in terms of applicability on the networks. Okay, and so scalability can be implemented by using different techniques. Maybe you have learned some of these on your network design course, but in terms of troubleshooting aspects, I'm covering those areas again. The layering and aggregation are two ways to optimize your network for the scalability. So you can divide the network, which we call aggregation, or separate the areas of the network and then add the areas when there are requirements. In this particular case, two techniques have been used to build a scalable network. One is layering, one is aggregation. A layered network allows different problems to be isolated from one another and resolved within the smaller set of parameters. You can build your network, large network, by aggregating it as small clusters. In this example, we named it as zone. So you have three zones, the several zones. The zone 1 and zone 2 are for the aggregation of zone 3 and zone 4, which means zone 3 is one of the smaller network. Zone 3 is a smaller network which is connected a certain number of machines. And zone 4 is another network which is another set of machines, and likewise zone 5, zone 6. There are four networks which are directly connected to the end user computers, but those are four separated. Likewise, we discussed on the VLANs. Assume that you have four different VLANs, so four different zones. So those zone 3 and zone 4 require to interconnect or intercommunicate. So now you have another zone which is to aggregate or interconnect these zone 3 and zone 4. Similarly, zone 5 and zone 6 have another requirement to intercommunicate, not only the intertraffic. So now you build another zone, which is zone 2, to aggregate or enable interconnection between zone 5 and 6. And later you have a requirement to intercommunicate between zone 3 and zone 5 as well, and zone 4 and zone 6 as well. Then you need to have another zone which is aggregating the previously aggregated layers, zone 1 and zone 2. So we divided three layers: access layer, distribution layer, core layer. This distribution layer is an aggregation points of the access layer zones. And the core layer is the aggregation point of the distribution layer zones. So you can implement routing policies on zone 1 and zone 3, and the traffic flows between four different zones are enabled. But core and distribution layers are overheads because those are enabling the communication between four layers, and it enabled the isolation as well. Let's say there is a DDoS attack on the zone 3. You can it may not going through affecting the zone 4 if you implemented the right technologies. So you can isolate the issues and troubleshoot that separately, rather than enable everybody having if let's assume that all the four zones, all the zones are integrated to single zone. If there is a DDoS attack, then every computer affected. So if you segment the network for small segments, then only one zone affected with a DDoS attack, it may not impacting to other zones. So then you can isolate that zone and troubleshoot and resolve the issue without impacting other zones. So this is reducing the blast radius, which we call blast radius of the network, by segmenting the network or isolating the network for small segments. Okay, that's the idea behind aggregation and the layering implementations. In this case, we heard three terms: access layer, which is the switch layer all the end user devices are connecting, and the distribution layer, which is for the aggregation of access layer switches, and the core layer, which is another layer you require with the scaling to aggregate different distribution layer switches. So this is a kind of a structure usually followed as design patterns when you are designing a large network with the scalability in mind. So to address scalability, you need to go on the layering plus aggregation designs to have this. You will be having definitely you will be having questions on assignments and as well as the final examination on this layering and aggregation. Even that's the practice on the past papers. This is another the real world example of with a high level design document and diagram, which is enterprise dual IP ISP internet edge. We will be discussing the dual ISP scenario later in the later as well. Enterprise dual ISP scenario, you are having you are connecting your network to two different ISPs. Let's assume that Dialog and Sri Lanka Telecom. If one service provider network fail, you can send your traffic through the secondary ISP or the another ISP. You can have couple of WAN edge routers. If one WAN edge router fail, another will take over. And you can load balance as well if there is a requirement. Some of the traffic can send through the ISP1 and some of the traffic can be sent through the ISP2. And there is you can for the load balancing and the failover mechanisms, you can implement dynamic protocol such as border gateway protocol for the WAN edge and between the service provider routers. And further, you can have a couple of firewalls to separate the WAN edge or the external network with the local area network and implement the sync cable between two firewalls to synchronize the state tables. If one fail, other will take over the functionality. So you have redundancy there on the firewalls with the high availability pair. And the state tables synchronized by using the interconnection cable, heartbeat cable. And then you have links between the router for each firewall. And your local the firewall separated trust boundary. And now you have internal network with the scalability introduced there. You have core layer switches, and the switches are interconnected by a peer link and link redundancy enabled there. And you have cross connections between distribution layer switches and the link redundancy enabled there by interconnecting all the switches as a full mesh, which means all the switches are interconnected with each other. And implemented the dynamic routing protocol named interior gateway routing protocol named OSPF, which you learned in the first semester design courses. And then the access layer switches are connected by the redundant link. Each is connected with the two distribution switches. If one link fail, traffic will go to the other links. And the three different VLANs. So the zones separated. So on the access layer switches, so intercommunication possible through the distribution layer as well as the isolation is provided through the VLANs. So this is a kind of design you can see in the real world with high level design document, HLD. So this is an example of how you implement. We will be discussing this in the details later. Okay, probably we can go for the break right now, and we can meet after the 15 minutes. I'll put up a timer on this. Right. Any questions you may ask now, or you can ask after the break as well.